Hello. Good morning and good afternoon, good evening from wherever you are in the world, and welcome to this C3S Energy Operational Service webinar. We are here in rainy Norwich in the UK to provide you with this exciting webinar on climate projections. So I will give you a brief overview about this C3S Energy Operational Service. I'll tell you a bit about the program of webinars we had and we will have, and then pass over to the excellent speakers we have today. So let's start with a bit of background, a bit of history about the C3S Energy. So C3S Energy Operational Service, and for those of you who don't know what C3S is the Copernicus Climate Change Service, which is an EU program operated by ECMWF in Reading, UK. And we are operating as agents for or contractors for ECMWF. So this is based on two previous proof of concepts, one called Clean for Energy on your left and one called ESEM on your right. And these were running before C3S Energy, which started in May 2018, and we are now over halfway, more than half the duration of the contract, which is 2 years. And so basically a year and a half into the project, and we got another about 6 months left on the current contract. So the two demonstrators, the two proof of concepts came together and provided the new service. And the rationale for the energy service, as it was also for the proof of concept, was to develop a climate service with and for the energy industry stakeholders, which means that we're listening to stakeholders from the energy industry. We've run a number of workshops and stakeholder workshops and received a lot of feedback, and we continue to do that. And what we heard is that people in the industry would like to have more than just capacity factors. So we are looking at energy variables, and this can be then easily applied when we compare, for example, demand and supply. We also heard that people are keen to bridge the gap of communication between climate and energy, involve a wider community in the conversation, so policymakers, strategists, but also students. So that we are developing this community around the topic of climate and energy, which is really timely and topical in the discussion around climate change, IPCC reports and the Paris Agreement and so on. So in a nutshell, what we are doing here, we are producing this operational service, which is providing variables or indicators for both climate and energy. And we do that for 3 streams. So we look at the past historical record, in this case from ERA 5 reanalysis produced by ECMWF under C3S. And this runs from 1979 to present. Then we have the second stream, which is seasonal forecast. And these two were already presented in previous webinars, which can be found on our website, and I'll give you the details later. And then we have the future, the climate projections, which is the focus of today's webinar. Both, so all the 3 streams are dealt with both with climate and energy indicators. So for all these 3 streams, you will find climate indicators such as temperature, wind speed, solar radiation, precipitation, and mean sea level pressure. And in terms of energy indicators, we have electricity demand, wind power production, PV, solar photovoltaic production, and hydropower, both in terms of run-of-river and reservoir. So a good set of indicators for people to get their teeth into the topic and start to see how things evolve over time and in the recent past, in the far future, up to 2100, but also with seasonal forecasts that provide an overlook of the next few months. The way we are progressing is that we set up this system, which is an operation system. So we need to look at all the specifics about how the system works regularly on an ongoing basis, and so we need to have a strict structure, strict conventions, and this will allow us to just operate almost without little control, human control. So we've in the first phase so far, we've developed most of the 3 columns you see from climate data, post-processing, conversion into energy variable. All most of this is being done already. The next phase will be to focus on how we display this information on a web interface. We did have the web interfaces, as I showed before, but we are going to update that, and so watch this space for the new web interface that will come live over the next months. So for today, we have the agenda. So we got an hour webinar in total. If there's enough interest, we'll continue also with question a bit over the hour, but let's see how we go. But we do have a great program here with Dr. Robert Vautard presenting. He's the director now of the IPSL Institute in France, and he's going to provide an overview of climate projections. Sorry for the spelling there, for energy. And then Dr. Flavio Pons is going to give us a bit of more of an insight on how the climate and energy projection indicators are produced under the C3S Energy service. And then we'll have question and answers. The webinar is recorded, so you will also see it online after, but do pay attention during the webinar and ask questions at any time. You can ask questions, I will take them, and then we'll respond to the question at the end of the webinar. So it's my pleasure now to pass over to our speakers, starting from Dr. Robert Vautard. Robert, over to you, please.
Thank you, Alberto, for the introduction. So, want to thank everybody to be online. Is the presentation okay on the screen, Alberto?
Let me check. Sorry, Yes, sorry. Yes. Working.
Okay.
Well, let's see.
Okay, thank you. So I will start this webinar, this presentation by which is designed to explain how we build climate projections for the future, which means the future starting a few years ahead to decades ahead until the end of the century, and to see how these projections can be useful to the energy sector also. So I will start with a recent result. You know that climate projections are produced by teams all around the world, by about 20 to 30 institutes all around the world. They are producing climate projections in a coordinated exercise with the same scenarios, the same assumptions, and comparing the different results from the models. And what the next slide that I'm going to show will concern the projections which are coming from the 2 French models. So I will be yes. So I'm sorry, this is a French slide in French. This is the only one in French. But essentially, this slide will show the result of, first of all, sorry. Yeah. So this slide starts with the observation from the 19th century up to now with the models, the two French models, which contain several simulations, 10 simulations from the Météo France model and 30 simulations from the IPSL model, and their average to show that these models follow quite well the historical observations. And once these observations are, these historical periods are produced, these models can produce future scenarios depending on the level of greenhouse gas emissions that, as you can see, diverge quite a lot after essentially 2050. So these are the results from only two models, the two French models, but there will be much more next year and also this year with all the groups all around the world producing such simulations. And from what we can say already from these projections is that, first of all, it's important to notice that we do not expect to have each event of each year exactly well represented in the global temperature. This is the global temperature, but essential is whether we can reproduce the trends and the climatologies of these temperatures. Another message also, I think, which is important, is that, as you can see in the projections, until 2050, there's not much difference between the scenarios. So essentially, the future, whatever we do on greenhouse gas emissions, is already almost settled until the middle of the century. It's really after the middle of the century that projections diverge. So this is the first thing. I started with the results, and now I'm going to explain a little bit more what how these projections are made with. So,
sorry, Robert.
Yes.
Sorry, I'm sorry to interrupt you. If it's possible to quickly change to full screen rather than, because we can see next slide. Sorry for everybody for interrupting. It's probably a bit distracting. If you can fix it quickly, otherwise it's fine to continue.
Oops. So yes, I am on full screen, but yes. So sorry, I will change maybe the problem is that the full screen does not open on the right window. So yeah, so
yeah, but it's
yeah, I think yeah, I think
Robert,
yes.
Laurent speaking. If you come back to your screen when you are in presenter mode, the one
Yes.
you had just before.
Yes.
So put the slideshow.
Yes,
Ouais, tu peux mettre en mode, vas-y, mets en mode diaporama.
Yes, that is. Can you see my presentation now currently?
Yes.
Yes, you can see it, but not in full screen.
Non, but vas-y, mets en diaporama.
Yes, there it is.
Et
But
là,
the
en haut,
problem is that
dans ta fenêtre, pas la plein écran, l'autre, tu as paramètres d'affichage. En haut là. Voilà, au milieu. Et là, tu dois pouvoir changer. Voilà, si tu fais basculer.
Okay, thank you so much, Laurent, for your experience on that. So I quickly switch back to the slide, and I'm sorry for this technical problem. Yeah, so the question, so this is the classical picture from IPCC, and the question is whether these projections can be used for the energy sector. So there are basically two types of use for which we can expect this projection to be useful. The first use is to predict the climate evolution and the distributions of the energy resource and demand. That concerns essentially resource in renewable energies, demand, of course, and also resource in water and also bioenergy, etc., etc. And the second type of use is to be able to assess climate risks in different periods of time. That is to say, assess whether we have an increasing risk of having less water in the rivers to cool the power plants, for instance, or whether we can have damaging events in the future, more damaging than the present or more frequent. And therefore, it's very important to use these climate projections but in combination with past observations. And climate risks are often taken from past observations. So climate is changing, and it's really important to use projection as well. So just in a nutshell, how these projections are made. They are usually made from global climate models on the left, which include all the components, the atmosphere, the ocean, the glaciers, the ice, and all the components of the atmosphere, so the greenhouse gases, but also the aerosols, ozone, etc. And it's important to have everything together because everything interacts together. So this is the global model, but often these global models have a scale resolution of about 100 kilometers to several hundred kilometers, and it's not enough in terms of resolution to get details to be useful. So there is usually downscaling, which is done using a kind of zoom of the same types of models, but at a more regional scale, which is with typically for Europe, we have projections at at about 12 kilometers, which are available. Currently, we have 35 to 40 models actually available at this scale of about 10 to 15 kilometers. But of course, if we want to go in the energy sector, then we need to have impact models, such as models of the river flow, the inflow for units for production of energy. So the second thing which is very important is that these models have biases. Each model have a different bias than the neighbor model. So it's very important to represent the full spread of possibilities that the models are used in combination, not just use one model. So the question is then, are climate models able to simulate the distribution of the key variables? The key variables are often temperature, wind speed, radiation, precipitation. Of course, there are other variables which may come into play, such as humidity, etc., but we will focus on these four ones. On this graph, on this plot, we show several models. So there's 10 plots on the top for the winter season and 10 for the summer season. On the top left corner is the observation, the mean observation, which is found over Europe of temperature, current temperatures. And all these other plots represent the biases, the mean biases of different models that are used for Europe. So you can see that these models, some models can be very cold in Eastern Europe and Russia, and some other can be warm instead. So it's very important to understand that these models have been developed separately and have different biases. So that is why we have to use an ensemble of models. For the summer, we have the same thing. So in order to be useful, we also have to get rid of these biases. And Of course, we cannot get rid of the reasons for these biases, but at least we can adjust the outputs so that they have a correct distribution. So there are statistical methods to do that. I'm just showing very schematically how the distribution, the model distribution, can be corrected to fit the observations. So we have to assess observations first and assess model, and then we can judge whether the model is too far from the observation to be corrected, or whether it can be corrected in a statistical manner. So once this step is done, in principle, the projections can be used. So the general facts about the capacity and the skill of models is that for temperature, models are representing well observation. They have biases, of course, but the variability is usually relatively well simulated, especially in the winter. But in summer, we have what we can say is that for Western Europe in general, models underestimate the trends which are observed. For precipitations, currently we have quite a good representation from models, a little bit underestimating the extremes, but we are generally happy with that. Surface wind speed, we have a tendencies of models to generally overestimate wind speed at the surface, but once again, it's not very far from reality, so it can be corrected. For radiation, the models by themselves simulate relatively well the radiation, surface radiation. So for variability, for studies of variability of radiation, it's fine. However, for future projections, there are strong uncertainties of across Europe about the future fate of the radiation. So just to show some trends for temperature, so climate is warming, and these two pictures show the trend between between the end of the century and the end of the past century, and before bias correction and after bias correction. So it's preserving the trend. We have, in this case, for this scenario, about 2 to 6 degrees. For precipitation, there is a general pattern of drying in the south of Europe and wettening in the north of Europe, whether we use models or bias-corrected versions of these models, and these trends are significant. For wind speed, it's a little bit more uncertain, and we do have some spots in Europe where we can find agreement among models, but this is here between the middle of the century and the end of last century. So generally, winds are decreasing a little bit in the south of southwest of Europe. And there are some spots where all models kind of agree of an increase, which is in the near the Greece, and there is also to some degree some agreement of models to have increasing winds in the Baltic Sea region. But these are small trends. We are talking about 5 to 10% at most. And these are, these are relatively small compared to the noise. For radiation, we have a lot of uncertainty. As I said, I do not have the time to explain, but all models seem to show a increase of radiation in Southern Europe. But in Central and Northern Europe, there is a strong disagreement among models. So we have to be very careful. So a few applications, and I'm going to show one of the results that we had a few, 1 or 2 years ago. this is essentially the application for, in this case, power production with different mixes, and this is for hydro in this case. So what you see in the graph is has been calculated from climate projections together with hydro production models, accounting for different power production units. And what we see is that essentially most of Europe have decreasing capacities or decreasing capacities to produce electricity with hydro, except in the Scandinavia countries, for which there is an increasing capacity due to the wettening trend. So these are the type of application. They need complex models to calculate that. And actually, we can do the exercise. So you cannot see all the details, but we can do the exercise, and we have done this exercise for future projections for the different technologies. I'm sorry, I was the previous slide was for all technologies together. So I'm sorry, I said the hydro, but that's for all technologies together. So we can split by technologies and see that, for instance, wind power have small changes, generally negative, except in some countries, and solar power generally negative with lots of uncertainty. Hydropower is more beneficial in Northern Europe, and thermoelectric is declining capacity due to a number of factors, but essentially river flow and river temperature. So there are also changes in risks across timescales, and current risks, as I said, are often based on past observations, and now these projections allow to take into account the future projections and not only use past observations. So basically, the interest of using several models, if we have, like, for instance, 10 models, is to have large sets for statistics. If we have 30, if we are considering a climate period of 30 years, and we have 10 models, that makes 300 years of statistics, so we can calculate extremes and see if the frequency of extremes will change in the future. So I'm just showing an example here as for cold spells. Cold spells are very important for demand. When there's a cold spell, there's a lot of electricity demand and energy demand in general. And these curves show, as a function of the return period, the return value of one index, which is Météo France heat index, which is basically an average of temperature over France, over 30 cities. And the blue curve shows basically the past climate and the past probabilities. The red one is the current, and the orange one is the future curve constructed with these models. So what we see from this graph is that cold spells will decrease in frequency for a given level of cold spell. For instance, the 1985 January cold spell. Then if we look at the statistics in the current climate, it's predicted to be twice less probable, and in the coming future, in the coming decade, it's twice less more. So this means that what we are saying is that these cold spells that we saw in the end of that we witnessed in the end of the 20th century are going to decrease in frequency, but not disappear. We are talking about a factor 4 compared to the last century. So we did a number of types of events. This one is the Seine River flood which occurred in June 2016, and we could assess the probability of such flood in the current versus past climate, and we could find that the probability of such flood, or at least such precipitation, has increased by a factor of 2, and this is shown by a number of models and model ensembles. So there is quite consistency here among the results. So yeah, so I have a number of other examples, but maybe just to show the last one, this is the typical problem that wind power producer could encounter, which is what we call wind droughts. And the question often is, this is a wind speed curve across years, and when you have one wind farm tested over some period here, and in operation in some other period, you may find some difference and sometimes be disappointed by the production, which is not exactly as expected. So the question is whether climate change has an impact on that. So the question is difficult. It's still a research topic, but what we can say at a relatively large scale and over Europe is that we generally have projections and comparison between current climate and past climate, which tend to show an increase of wind droughts here of seasonal scale. So this is also in line with the projections finding. So looking ahead, and before to conclude, what we can say is that the current status of climate models is to represent the climate relatively well, with some, of course, with some biases that we are understanding more and more at a typical scale of 10 to 15 kilometers. But now we are developing models with convection, which is the big clouds, the thunderstorm clouds, which are resolved explicitly. So typically simulations with 1 to 5 kilometer resolutions. And these are still research tools. We do not recommend to use them in climate mode at the moment, because we need more research to understand what this does. And this is typically an application for extreme 3-hour precipitation amounts. So these are observations along the Mediterranean coast, simulation of these precipitation average with a 12 kilometer and with a 3 kilometer resolution. So we have really good hopes that these models at this resolution will improve a lot the climatologies. Okay, so as conclusions, the ensembles of climate projections can be used in practice for the energy sector, provided that we are a little bit careful about a few things. Some variables like radiation, may not have a very robust signal for the future. There's still research to understand that. Bias adjustment and model selection is important, and they can be used for changes in resource for renewables, and also for changes in risks of due to extreme events such as extreme precipitation, heat waves, and other types of extremes. So thank you. I hope that I have convinced you that these projections can be used with some care. And I will give the floor to my colleague, but maybe Alberto wants to say a few words.
Excellent. Thank you very much, Robert. was an excellent introduction, and we are already receiving some questions. So I invite everybody to put your questions to the question tab on your GoToWebinar control panel.
Yes.
And we'll take them at the end. But we are now moving to presentations, and we'll learn a bit more about how the climate and energy indicators are produced within the C3S Energy operational service. So over to you, Flavio. Thank you.
So I'm sorry, I need to, yes, okay.
Thank you, Alberto. Hello to everyone. So what I'm going to do now in this presentation is to try to give you an idea of what we produce actually in the projection stream and how, basically going through the workflow of our projection stream. So this is a snapshot of the whole workflow. We will try to go through all the steps and see what kind of files come out from these and how they are produced. So as you can see, the first step consists of data retrieval. And as Robert mentioned, model selection is important here. So we have an ensemble of models. We will see in a minute which ones coming from your Cortex. And basically, the first step is to ask for raw data that are made available in different ways, either through ESGF or FTP servers or other repositories, and these are always netcdf files. We have 4 variables mentioned by Robert, and here I highlighted 2 different name conventions. In black, the ESGF convention, and in red, our data management plan convention that you will find in some of the outputs. These models, at the beginning, they are on a 0.11 degrees grid centered over Europe, and the time frequency is 3 hourly for all variables, so radiation, wind, and temperature, and daily for precipitation. So when we receive these models, each month, hour of the day, or year, this can be disentangled in different ways depending on the production. And the first thing we have to do is to merge all of these, and we use CDO for this step. CDO is a collection of commands to handle netcdf files, and it also admits an interface with Ruby and Python, so it can be convenient if you want to use one of these languages for your processing. Here is the selection of models for our first year. So this is already, we already finished the production for these ones. And as you can see, we have 9 combination of global and regional circulation models. And for all of them in the first year, we merged historical with projections under RCP 4.5 and 8.5 scenarios. However, in the second year, we are going to have more models. And for some of them, we also include, or we include instead of RCP 4.5, RCP 2.6, just to see a less extreme scenario, how it behaves. And after this phase of collection and preparation of the data, we have the bias correction that was already mentioned by Robert. And this is necessary because each model has different parameterizations inside, so each model develops a different bias on different variables. We choose this cumulative density function transform approach, where we basically consider the period over which we have also ER5 reanalysis. We compare each model with the reanalysis, and we learn a mapping of the distribution function of the model on these past values, and we apply the same transformation to the future to correct the model output. So this technique assumes that the process is stationary in time, and we do it pointwise on the grid, which means that we also assume implicitly a spatial independence. So how to deal, we do not deal with spatial dependence in any explicit way. However, since it is done pointwise, we preserve at least some spatial structure. And instead, to deal with time correlations and trend, we separate hours of the day and month. So we deal with the daily and seasonal cycle, and we perform the bias correction over a rolling window of 20 years, retaining only the central 10 years as a result to avoid problems with long-term trends. And while we do this, we also remap everything on the same grid as ERA5, which is a 0.25 degrees grid. Bias correction for now is still a very heavy task, and it runs with 4 transcripts at the moment. So at the end of bias correction, we actually have ready our gridded climate indicators, but we also perform a spatial aggregation. And in particular, we choose the NUTS aggregation specified by Eurostat, choosing NUTS 0, which means country level, and NUTS 2, which means regional. So basically, this aggregation can be seen as a weighted average of our variable of interest, where the weights will specify the region. How we do this is we take shape files from Eurostat, and we create 0-1 masks with the shape of each region. And then we take the Lancy mask, the Lancy mask provided by the Met Office, which tells you the proportion of water to land in each grid point. And we mask the Lancy mask using this shape file. And finally, we apply cosine latitude weights to account for the effect of curvature. This is done again with CDO for the projection stream. However, this can be enveloped in a Python script. And the result of this step are again netcdf files, but we further process these netcdf files using Python now, so that we can write CSV files that will be available on the demonstrator. And in particular, we follow a specific structure dictated by our DMP, so that we have metadata on the top of the first column, and each line starts with an hashtag, so that when you import this data with R or Python, you can look at these lines as comments and ignore them. And below that, you have the actual data. The date is in the first column, and here we also transform every calendar that we possibly have to a standard one, because we have 360 and 365 days calendars in the model depending on the institute. And finally, in the rest of the files, you have one column for each region, and each column name is the Eurostat name of the region. So at this point, all the climate indicators are ready and are ready to go on the demonstrator and to be used for the production of energy indicators, which is the next step. So the methods have been already discussed in our webinar number 2 that consisted of, I think, 3 presentations. So to have more details, you can go back to that or ask some questions now if you want, and we may have a further webinar about energy modeling in the future. So basically, the energy part is divided in 2 substreams, and in one we produce gridded indicators again, and in one we only produce NUTS 0 aggregated indicators, and I will start from this. In this part, we have a modeling for energy demand and a model for hydropower, and both are handled by statistical models. So demand in particular is handled using generalized addictive models, and if you don't know this, it's basically like a linear model where a variable is passed after being transformed with a spline, so it's a bit more general. And here you have a snapshot from the webinar number 2 that is actually a reconstruction of the hindcast and not of the projection, but the principle is the same. So you can train these models over a period where you have observations and reconstruct or forecast unobserved data. And the input of this model consists of temperature, radiation, wind, and some calendar variables. The hydropower is obtained with a statistical model as well, but in this case it's a random forest that is a collection of decision trees, and this can be used for classification or regression. Here, of course, it's used in regression mode so that we can forecast, and we do it separating, like Robert already mentioned, runoff river and reservoir. Okay, so these and also demand are obtained through R scripts, this by Lin O and demand by Laurent Dubout, and the results are CSV files with daily NAT0 data. And these are ready to go to the demonstrator like this. Furthermore, we have this part of the stream where we produce gridded energy indicators at 3-hourly frequency, and these rely rather on physical models and not on statistical models. So starting from the wind, this is very simple because it basically consists of applying power curves of typical wind turbines to the wind speed predicted by the climate models. Here we have we take the power curves of Vestas turbines, and these are taken from the windpower.net, that is an online database of power curves. And we separate onshore and offshore because, of course, the wind field has very different features over the ocean and over land. The main problem here is that, of course, we need the wind speed at the turbine height, so at 100 meters. And while we do have that in the reanalysis, we do not have these in the climate projections. So we estimate the wind at 100 meters using a simple relationship that, however, requires to estimate this alpha parameter, that is some roughness parameter. So we did it using Euro 5 between 2000 and 2017. We may as well repeat it using the whole period that is available now. And then we compute wind at 100 meter. This way, this is a map of the values of this coefficient, and you can see you have huge differences between the ocean and land. And on the ocean, the field is very uniform, and and on land is 50 to 100% larger and less homogeneous. So what we did is we kept the values of alpha point by point on the grid, but we averaged in time. We actually observed some time variability depending on season and on meteorology, but for now we decided that this spatial structure is enough. And the result is we apply basically these power curves to the 3-hourly gridded wind data, and we obtain 3-hourly gridded wind power capacity factor, that is a non-dimensional number between 0 and 1. This also runs with an R script, and this file contains also metadata with a convention that we have in our DMP. And for now, the file name convention for the gridded energy indicators is the same as the climate indicators that go on ESGF rather than the DMP convention that we use for the NUTS files. Finally, passing to the solar power capacity factor, this is a bit more complex of a model, and this has been defined by Yves and Renan, and has been discussed in one of the presentations of webinar number 2. So I invite you to go there and look at it if you are curious. But however, we have a physical model in this case, even though a part of it is still a statistical parameterization. And we have this part. I will not go in the detail of this, but this is the more complex part. And operationally, the operational version is still quite complex, with 16 coefficients that we compute again point-wise on our grid. And okay, this is a model that proved to work very well. It shows very high correlations between target and predicted values for periods where, of course, we have observations. Again, you can find more detail in this previous presentation here. And this is obtained using a Python script. Since in this case, the time of the year and the hour of the day are important, we keep the calendars for the moment. We did it keeping the calendars that are in the model. So the output will be on a 360 or 365 days or standard calendar. So the results at this point are gridded 3 hourly energy indicators. We further process these with the same NUTS averaging that I already described. And with this is the last step of our workflow concerning energy indicators, and all of these are now ready to go on the demonstrator as well. So to sum up, from the talk by Robert, we saw that there is a lot of science behind all of this, but in the end, we have also a lot of data in our hand, and we must treat it carefully. And also, all our products are data sets, basically. So it's important that we are transparent, and this is why we do these webinars, to explain what happens. There will be documentation associated to these data sets, and they contain metadata as well. And okay, so to sum up, we have this phase of model selection and preparation, and from these we obtain gridded climate indicators, and transforming these we obtain also gridded energy indicators, and then both of these are made available as aggregated time series, plus at the same level we have hydropower and demand modeling. And I think these files are of course, they contain less information, but they are very handy to do a lot of statistics, at least over Europe. So I conclude and thank you for your attention.
Okay, excellent. Thank you very much, Flavio and Roberto. I'd like to thank from everybody with an applause. Yeah. Okay, and virtual applause for you, and like to now move to questions. So I'm going to show, we've received already some questions. I'm going to show them to you, and then if other people want to ask questions, please feel free to just use the panel, control panel. So I'm going to switch now. I can find where to do it. Okay, so you're seeing now the questions that have come in, and this were for the first part still. So mainly to Robert. The first question from Denisa is which short-term scenario is assumed until 2050, Robert?
So in this, so there are different answers for that, but I would say in the service there will be basically two scenarios. One which is the RCP 8.5, which is supposed to be the business as usual scenario, without much care about climate, and the other one will be maybe I don't know if it's going to be more realistic, but RCP 4.5, and we are also for a few models now including a scenario which would go in the end of the century to about 2 degrees, which is the RCP 2.6. However, I think it's important to notice that until 2050, the scenario doesn't matter much. More or less, the future is already written because of some because the emissions are not going to stop tomorrow. It will take some years, hopefully not 30 years, but they will go. They should go down, but the pace at which they are capable of going down is not so high. So the scenarios, the answers will be not so much different in the different scenarios until 2050.
Okay, thank you. Yeah, so I'm going to read the question to everybody. So Keith is asking, to what extent do you think the latest development from the Met Office, the UK SIP 2.2 kilometer resolution models, will be a game changer? And how far away are we from models at that spatial resolution across the whole of Europe and beyond? Robert. So
yeah, it's a very important question. There are now several groups doing 1 to 5 kilometer resolution models. I think there is still, so it's interesting to use them, and but with a lot of care, because at the moment, and as I explained, it's usually we have to explore future with different models, not with a single model. So that would be the advice for users that I would say. And also, I think it's important to understand that we have not, there's a lot of research about this type of models. It's not because we just increase the resolution that the models are becoming suddenly better. There are many parameterization in models, such as the parameterizations of the droplets, of the physical processes, the interactions between the land and the atmosphere. And these parameterization, these assumptions are providing different results at different resolutions that we may not fully understand today. So I do think that these types of simulations will be game changers because of, especially on the water cycle. But we still don't, we don't understand fully these changes yet. There's a lot of research going on.
Okay, thank you, Robert. And I may also ask, while we're waiting for other questions, sorry, could you comment also on the projections that you showed at the beginning with the global projections up to 7 degrees temperature increase? Have they been bias adjusted, or they just anomalies compared to the past? And the second question, more, I think it's more political in a sense, but I mean, there's a delicate message there, yeah. When you say that there's no major change between the scenarios up to 2050, we, you know, some people may look at them and say, okay, so what can I do to try to improve? Because I can see there's no, I'm not going to make any difference up to 2050, and yet beyond, you know, you can make a big difference. So I think it's important to position the message carefully there, isn't it?
Yes, it is. You are absolutely right to raise this point. I think it's important to understand that what we are doing now, we are acting on the time derivative. So in a scientific word, so essentially, what we are doing now, the changes that are urgent now will have an effect later, but the lack of action will also have an effect. So it will really, what we have to do for the next decade is strongly strengthen adaptation, because we know that the future is going to warm at least to 1.5 degrees above pre-industrial, and probably more, depending on what is done and at what scale. But it's very important to understand that these actions on greenhouse gas emissions are, of course, we won't see the changes immediately, but they are affecting future generations. So it's and current generations actually of child. So we see movements from young people currently taking on board this message. Relative to your the first part of your question, I'm sorry, Alberto, can you repeat it?
Yeah, it was simply whether there was any adjustment on the value you showed or not.
No. So these figures we have showed them at a press release last week. Of course, there was a lot of buzz about this 7 degrees or so. So you have to understand that it's relative to pre-industrial. It's not relative to today. And it's also the worst case scenario. And we have to be a bit careful with these projections. There are different scenarios. Some scenarios go also to 2 degrees. And yes, though there is no bias correction on these figures. It's just anomalies relative to the 19th century. And I think this will also be, you know, we are looking at differences between the previous generation of models and the current generation of models. So we need to be a bit careful at this stage, of course, to compare. What we see in general is a slight increase in the sensitivity of models. But we have to be careful and wait for the assessment of the ensemble, which is, I think, the articles, the scientific articles, are going to come in the coming months or so, and we have to really follow this literature, because yes, we think there will be some changes.
Okay, thank you, Roberto. Last question we're going to take today is from Abdullah, and I don't know whether you or Flavio want to answer. I can also provide my quick answer to this. I'm following from Africa, but this look more Europe focused. How can you support the production of such data sets for Africa?
Maybe you want to answer first, Alberto, on this one. I can follow, of course, but.
Okay, so thank you, Abdullah. So yes, we, as you correctly noticed, the products we are producing are for Europe, and probably should have highlighted also at the start with my presentation. But this is because the program is providing the funds to develop this for Europe at the moment, but we've received a lot of requests, and we're also working on various proposals to extend this to Africa, in fact, and other continents around the world. So we're working on that, but it's also the case that we want to learn well what can be done for one continent like Europe, and then we are more confident to extend to other parts. We will always have problems with especially energy data for some countries, but even in some countries in Europe. But we're learning how to deal also with lack of data. That's why it's important to have this first phase in Europe. Maybe Robert, you want to add as well?
Yes, I'm not talking about the energy side, but in terms of regional climate projections, I know that Copernicus is interested in producing data sets also for other regions, including Africa. So it's not currently available for regional projections. It's available from global projections, but not from regional projections at the moment from Copernicus Climate Change Service. But it is intended to be done in the near future. So I cannot tell exactly the time scale, but I would tend to say it's in the order of a year or so.
Okay, excellent. So we are receiving other questions as well, but I would like to stop here. We're already a bit over time, and just want to give you also a couple of other pieces of information regarding the upcoming webinars. So we have, this was our 4th C3S Energy webinar. The 5th one is it's going to be on Monday, 14th of November currently, and this is going to be on the case studies for energy. And then we'll have additional ones after that to be announced. And all the recordings are available on online. You can find them at the link you see here, both on the WEMC website and the C3S website.